This is a photograph of an outcrop of metamorphic rock exposed on a hillside in Scotland. It displays contorted foliation and contains minerals that formed at high pressure and temperature at depth in the crust. James Hutton, the man who came to be known as the father of geology, examined these very same outcrops, hoping to learn how rock formed. Hutton discovered that many features in the outcrops resembled the products of present-day sediment deposition or volcanic activity, and from this observation he came to an understanding of how sedimentary and igneous rocks formed. But Hutton also recognized that some rocks contain minerals and textures quite different from those visible in sedimentary and igneous rock. He described this puzzling rock as a mass of matter which had evidently formed originally in the ordinary manner, but which is now extremely distorted in its structure and variously changed in its composition. The rock that so puzzled Hutton is now known as metamorphic rock, from the Greek words meta, meaning change, and morph, meaning form. In modern wording, a metamorphic rock forms when a pre-existing rock, or protolith, undergoes a solid-state change in response to the modification of its environment, generally at depth in the earth. We use the word metamorphism for the overall process of such change. By solid state, we mean that a metamorphic rock does not form by solidification of magma. Remember that geologists consider rocks that solidify from magma to be igneous. By change, we mean that metamorphism produces new minerals that did not occur in the protolith and produces a new texture or arrangement of mineral grains that differs from that of the protolith. By modification of the environment, we mean that metamorphism takes place when a protolith endures a rise in temperature or pressure, undergoes compression and shear, or reacts with the hydrothermal fluids, solutions of very hot water. And by using the term at depth, we mean that metamorphism takes place at higher pressures and temperatures than those responsible for diagenesis. Metamorphism can produce a group of minerals that together make up a metamorphic mineral assemblage. Metamorphic rocks have metamorphic texture, defined by the arrangement of their mineral grains. That texture can be manifested by metamorphic foliation, which is characterized by the parallel alignment of platy minerals such as mica, or by the presence of alternating light-colored and dark-colored layers. Metamorphism of red shale can yield a metamorphic rock consisting of aligned mica flakes and brilliant garnet crystals. For example, in our photograph, a specimen of red shale on the left contains clay, quartz, and iron oxide. When this rock undergoes intense metamorphism, it may change into a gneiss, G-N-E-I-S-S, containing different minerals. The gneiss sample right contains biotite, quartz, feldspar, and purple garnet. Metamorphism of limestone composed of cemented together fossil fragments can yield a metamorphic rock called marble, consisting of large interlocking crystals of calcite. As seen through a microscope, the change in the grains of a rock can be very dramatic. Note the interlocking crystals of the metamorphic rock on the right. Metamorphism often creates foliation, a texture defined by the alignment of platy minerals or by the creation of alternating light and dark bands. On the left, we have a granite protolith, and granite, when it undergoes metamorphism, becomes similar to the image that we see on the right, in which the feldspar crystals are almost parallel to one another. The formation of metamorphic minerals and textures takes place very slowly. It may take thousands to millions of years and involves several processes which sometimes occur alone and sometimes together. The first process, recrystallization, changes the shape and size of grains without changing the identity of the mineral making up the grains. For example, during recrystallization of sandstone, a tightly fitting mosaic of large, irregularly shaped quartz grains, the metamorphic rock, replaces a cluster of small, round, cemented together quartz grains, the protolith. Phase change is a metamorphic process that transforms one mineral into another mineral with the same composition, but a different crystal structure, what we call a pseudomorph. In this example, andalusite can change to sillimanite, or it can change to kyanite, depending on the amount of heat and pressure that the original mineral undergoes. Another process, neocrystallization or metamorphic reaction, results in the growth of new mineral crystals that differ from those of the protolith. During neocrystallization, chemical reactions digest minerals of the protolith and grow new minerals of the metamorphic rock. For this process to take place, atoms must slowly diffuse or migrate through solid crystals or dissolve and precipitate at grain boundaries. Pressure solution happens when a wet rock is squeezed more strongly in one direction than in the other. Mineral grains dissolve where their surfaces press against their other grains, producing ions that migrate through the water to precipitate elsewhere. Precipitation may take place on faces where the grains are squeezed together less strongly. Pressure solution therefore can cause grains to become shorter in one direction and longer in another. For pressure solution to take place, liquid water film must coat every grain's surfaces during compression. Such films can persist during diagenesis and during low temperature metamorphism. At high temperature, water molecules evaporate or break apart, so the film disappears. Plastic deformation happens when a rock undergoes squeezing or shearing at elevated temperature and pressures, conditions during which minerals behave like soft plastic and can change shape without breaking, as we see in the example below. What are the agents that cause metamorphism? They are heat, pressure, compression and shear, and hot water. Any one agent can cause a metamorphic change, but more often multiple agents occur simultaneously or over a long period of time. Consequently, the rocks may be overprinted by multiple events or multiple metamorphisms. Metamorphism takes place at temperatures between those at which diagenesis occurs and those that cause melting. Roughly speaking, this means that most of the metamorphic rocks you find in outcrops on continents formed at temperatures between 250 degrees centigrade and 850 degrees centigrade. The depth in the earth at which metamorphic temperatures exist depends on the geothermal gradient, which in turn reflects the geologic setting. The geothermal gradient for continental crust away from any intrusions is about 25 degrees centigrade per kilometer, and metamorphic temperatures occur only at depths greater than about 12 kilometers. Most metamorphic rocks that occur in outcrops on continents were metamorphosed at pressures between 3 and 12 kbar. That's equal to 3,000 to 12,000 bars, where 1 bar is the air pressure at the Earth's surface. Pressure increases with depth at a rate of about 300 bars per kilometer. due to the weight of the overlying rock. So metamorphic pressures occur at depths between 10 and 40 kilometers. Some metamorphic rocks, however, form at pressures that indicate that they were once even deeper than 40 kilometers. Metamorphic rocks formed under pressures between 12 and 27 kbar are known as high-pressure metamorphic rocks. Metamorphism under such conditions transforms mafic protoliths such as basalt or gabbro into eclogite, a rock composed of brilliant maroon garnets embedded in a greenish pyroxene. If the pressure at the time of the metamorphism exceeds 27 kbar, ultra-high pressure, UHP, metamorphic rocks form. In such UHP rocks, quartz transforms into a denser mineral known as coesite, and graphite becomes diamond. The pressure needed to form high-pressure or UHP rocks can probably develop only in crust that has been dragged down to Earth by the process of subduction. How such rocks can return to the Earth's surface remains a subject of research. In reality, pressure and temperature in the Earth change together with increasing depth. For example, at a depth of 8 kilometers, temperatures in the crust reaches about 200 degrees centigrade, and pressure reaches about 2.3 kbar. If a rock at 8 kilometers later becomes buried to a depth of 20 kilometers, as can happen during mountain building, temperatures in the rock increases to more than 500 degrees centigrade and pressure increases to about 5.5 kbar. Experiments and calculations show that the stability of certain minerals, that is, the ability of a mineral to form and survive, and of mineral assemblages depends on both pressure and temperature. Therefore, a metamorphic rock formed at a depth of 8 kilometers does not contain the same minerals as one formed at 20 kilometers. We can illustrate the relationship of mineral stability to pressure and temperature by studying the behavior of the compound aluminum silicate, as portrayed on a phase diagram. A phase diagram is a graph with temperature indicated by one axis and pressure indicated by the other. Aluminum silicate can exist as 3 different minerals: kyanite, andalusite, and sillimanite. These are polymorphs. Each of these minerals can survive only under a specific range of temperatures and pressures, indicated by an area called a stability field on the phase diagram. If geologic processes move a protolith containing the elements necessary to produce aluminum silicate to a depth in the earth where the pressure reaches 2 kbar and the temperature rises to 400 degrees centigrade, point X, then andalusite grows. If the temperature stays at 450 degrees centigrade, but pressure on the rocks increases to 5 kbar, point Y, then andalusite becomes unstable and kyanite grows. And if the pressure stays at 5 kbar, but the temperature increases to 650 degrees centigrade, point Z, then sillimanite grows. So the presence of one of these minerals provides a clue to the pressure and temperature in which the metamorphism occurred, and that is the presence within the metamorphic rock of one of these minerals can tell us what pressure and temperature range in which that metamorphism occurred. Put a ball of dough on the floor, lay a book on it, and step on the book. You'll see the ball flatten into a pancake oriented parallel to the floor, because the downward push you apply with your foot exceeds the push provided by air in other directions. If a material is squeezed or stretched unequally from different sides, we say that it has been subjected to differential stress. In other words, under conditions of differential stress, the push or pull in one direction differs in magnitude from the push or pull in another direction. There are two kinds of differential stress. Normal stress. Normal stress pushes or pulls perpendicular to a surface. We call a push compression and a pull tension. Compression flattens a material, whereas tension stretches a material. Shear stress is the second kind of differential stress. Shear stress or shear moves one part of a material sideways relative to another part. If you place a ball of dough on a table and set your hand on top of it and move your hand parallel to the floor, you're applying shear to the ball. Or if you have a stack of cards and you place your hands on top of it and shove it in one direction, you're applying shear to each of the cards within the stack of cards. Compression and shear at metamorphic temperatures and pressures may cause a body of rock to change shape without cracking or breaking. During the process, a preferred orientation develops in that pancake-shaped or platy grains become aligned with one another, as do cigar-shaped or elongate grains. Platy and elongate grains are examples of inequant grains, in that they have different dimensions in different directions. In contrast, equant grains have roughly the same dimensions in all directions. In wet rocks at relatively low temperatures, pressure solution dissolves grains on the faces perpendicular to the direction of compression. So as a result of pressure solution, grains become shorter in the direction of compression. Sometimes precipitation of new mineral crystals takes place on the faces where compression is less, so the grains may effectively get longer in the direction perpendicular to compression. At relatively high temperatures, weaker grains flatten by means of plastic deformation due to differential stress. The grains become more narrow in one direction and become longer in the other. Shearing either rotates inequant grains into alignment with the direction of shear, like logs in a river that align with the current, or smears and flattened grains. Growth of new metamorphic minerals during shear contributes to the development of preferred orientation. The new minerals grow faster in the direction in which a rock is stretching than in the other directions. Metamorphic reactions commonly take place in the presence of hydrothermal fluids. Hydrothermal fluids react chemically with rocks by dissolving, transporting, and providing ions. These fluids also provide water molecules that can become incorporated in minerals. In some cases, hydrothermal fluids passing through a rock during metamorphism pick up some ions of one element and drop off ions of another, changing the overall chemical composition of the rock. When this happens, we say that the rock has undergone metasomatism. Some originate as groundwater that enters the crust at the Earth's surface and then sinks downward. Some is released from magma when the magma rises, and some water originates as the product of metamorphic reactions themselves. Some react locally with other minerals within the rock, and they become incorporated into new minerals there nearby. Others precipitate in spaces that open up where rocks crack, producing a mineral-filled crack known as a vein. Veins commonly contain milky white quartz, so they stand out against darker colored rocks surrounding them, as we see in this image on the slide. The term foliation comes from the Latin folium for leaf. Geologists use foliation to refer to an assemblage of parallel planar surfaces in a metamorphic rock. Foliation can give metamorphic rocks a striped or streaked appearance in an outcrop. A foliated metamorphic rock has foliation either because it has preferred orientation, That is, it contains inequant mineral crystals that are aligned parallel to one another, or because it has alternating dark-colored and light-colored layers. There are two major subdivisions of metamorphic rocks, foliated and non-foliated. Foliated rocks are then divided into 6 subcategories: slate, phyllite, metaconglomerate, schist, gneiss, and migmatite. The first we're going to talk about is slate. Slate is the finest grained foliated metamorphic rock. It forms by metamorphism of shell or mudstone, rocks composed of clay under relatively low pressures and temperatures. Slate contains a type of foliation called slaty cleavage, which allows it to split into thin sheets that make excellent roofing shingles, as we see in the figure on the right. Slaty cleavage develops when compression causes clay flakes to reorient and grow in an orientation roughly perpendicular to the direction of compression. For example, horizontal compression of a sequence of horizontal shell beds produce vertical slaty cleavage, the image on the left. Commonly, such compression also causes the layers to bend into curves called folds. Phyllite is a fine-grained metamorphic rock with a foliation caused by the preferred orientation of very fine-grained white mica. The alignment of translucent fine-grained mica gives phyllite a silky sheen known as a phylitic luster, as we see on the image on the left. Phyllite forms when slate is heated to a temperature high enough to produce a new assemblage of metamorphic minerals, such as the fine-grained white mica, out of clay. Under the metamorphic conditions that produce slate or phyllite, if the protolith is a conglomerate, a sedimentary rock called a conglomerate, it becomes a metaconglomerate. Typically, pressure solution and plastic deformation flatten pebbles and cobbles of the conglomerate rock into a pancake-like shapes. The alignment of inequant class defines the foliation, as we see in the figure in the image. Schist is a medium to coarse-grained metamorphic rock type that possesses a type of foliation called schistosity, defined by the preferred orientation of large mica flakes, such as biotite or muscovite. Schists form at temperatures even higher than those needed to form phyllite, and it differs from phyllite in that it has larger mica grains. Typically, schists also contain other minerals such as quartz, feldspar, garnet, staurolite, and amphiboles. The specific mineral that grows depends on the chemical composition of the protolith. Schists can form from a shell protolith, but also from a great variety of other protoliths, as long as the protolith contains the appropriate elements to make mica. In some cases, certain mineral grains in schists grow to be much larger than surrounding grains. For example, garnet crystals in schist may become many times larger than those of other minerals. We refer to those as being porphyroblasts. Gneiss, GNEISS, generally forms at temperatures and pressures even higher than those that give rise to schists. The metamorphic rock type has layers of differing mineral composition, manifested by alternating darker and lighter colored bands. Typically in rocks with such compositional layering, the layers range in thickness from millimeters to meters, and their presence gives the rock a striped appearance known as gneissic banding. The contrasting colors in gneiss represent contrasting mineral composition. Light-colored layers contain predominantly felsic minerals, such as quartz and feldspar, whereas dark-colored layers contain predominantly mafic minerals, such as amphiboles, pyroxenes, and biotite. If gneiss contains mica, the mica-rich layers typically display schistosity. Gneiss can form from either sedimentary or igneous protoliths. How does banding in gneiss form? If the rock has a sedimentary protolith, the banding may evolve from the bedding, because the composition of a metamorphic band reflects the composition of the bed from which it formed. Banding can also form by extreme shear of a non-homogeneous rock, whether the protolith was sedimentary or igneous, if the rock accommodates the shear plastically without breaking. Such plastic flow stretches, folds, and smears out pre-existing compositional contrasts in the rock and transforms them into line sheets. Gneissic banding can develop by an incompletely understood process called metamorphic differentiation. This process may involve dissolution of minerals in some layers and migration or diffusion of the chemical components of these minerals to other layers, where new minerals then grow. In effect, chemical reactions segregate different minerals into different layers. If the temperature rises high enough, gneiss may begin to melt, producing felsic magma and residual still solid mafic metamorphic rock. If the melt freezes again before flowing out of the source area, a mixture of igneous rock and relic metamorphic rock called migmatite forms. Plastic flow during the process can contort the light-colored felsic rock and the dark-colored mafic rock into complex shapes. Nonfoliated metamorphic rocks contain minerals that recrystallize or grew during metamorphism, but the rock overall has no foliation. The lack of foliation means either that metamorphism occurred in the absence of compression and shear, or that most of the new crystals are equant. Some of the more common types of non-foliated metamorphic rocks are hornfels and amphibolites, quartzites, and marble, which we will discuss now. Hornfels are fine-grained non-foliated rocks that contain a variety of metamorphic minerals. The specific mineral assemblage in a hornfels depends on the composition of the protolith and on the temperature and pressure of the metamorphism. Inequant minerals that grow in hornfels are randomly oriented. In other words, they do not display a preferred orientation. Amphibolites, metamorphism of mafic rock, such as basalt or gabbro, can't produce quartz and muscovite, for these rocks don't contain the right mix of chemicals to yield such minerals. Rather, they transform into amphibolite, a dark-colored metamorphic rock containing predominantly hornblende, a type of amphibole, and plagioclase, a type of feldspar, and in some cases a tiny bit of biotite. Where subjected to differential stress, amphibolites can develop a foliation, but the foliation tends to be poorly defined because the rock contains very little mica. Most quartzites forms by the metamorphism of pure quartz sandstone. During metamorphism, pre-existing quartz grains recrystallize, yielding new, larger grains. In the process, the distinction between cement and grains disappear. Open pore space disappears, and the grains become interlocking. When quartzite cracks, the fractures cut across grain boundaries. In contrast, fractures in sandstone curve around grains. Quartzite looks glassier than sandstone and does not have the grainy sandpaper-like surface characteristic of sandstone. Depending on the impurities it contains, quartzites can vary in color from white to gray, purple, or green. Most quartzite has no foliation because it does not contain aligned mica or compositional layering. The metamorphism of limestone yields marble. During the formation of marble, the calcite composing the protolith recrystallizes, so fossil shells, pore space, and the distinction between grains and cement disappear. Marble, therefore, typically consists of a fairly uniform mass of interlocking calcite crystals. If the original protolith contained layers with different impurities, the resulting marble has color banding that makes it a prized decorative stone. Marble can flow like soft plastic under metamorphic conditions, a process that smears out different colored portions of marble into beautiful contorted curving bands. Up to this point, we've emphasized the importance of temperature and pressure in determining the mineral assemblage in a metamorphic rock. Let's not forget that composition of the protolith plays a key role in determining which minerals form as well. For example, it's impossible to form a biotite-rich schist from a pure quartz sandstone because biotite contains elements such as iron that do not occur in quartz. To distinguish among different compositions found in metamorphic groups, geologists have divided them into 4 broad compositional groups or terms: pelitic, mafic, calcareous, and quartzo-feldspathic. Pelitic metamorphic rocks form from a sedimentary protolith composed of shell or mudstone. The clay in shell or mudstone contains a variety of elements, including aluminum. So pelitic metamorphic rocks contain aluminum-bearing minerals such as muscovite, mafic metamorphic rocks contain relatively little silica and an abundance of iron and magnesium. During metamorphism, iron and magnesium-rich minerals such as biotite and hornblende grow. Calcareous metamorphic rocks form from calcium-rich sedimentary rocks or limestone and contain calcite, calcium carbonate. Quartzo-feldspathic metamorphic rocks form from protoliths such as granite that contain mostly quartz and feldspar. Not all metamorphism takes place under the same physical conditions. For example, rocks carried to a great depth beneath a mountain range undergo more intense metamorphism than do rocks closer to the surface. Geologists use the term metamorphic grade in a somewhat informal way to indicate the intensity of metamorphism, meaning the amount or degree of metamorphic change. Metamorphic grade depends primarily on temperature because temperature plays the dominant role in determining the extent of recrystallization and neocrystallization that takes place during metamorphism. Metamorphic rocks that form at relatively low temperatures, between 250 degrees centigrade and 400 degrees centigrade, are low-grade rocks, and metamorphic rocks that form at relatively high temperatures, over 600 degrees centigrade, are high-grade rocks. Intermediate grade rocks form at temperatures between these two extremes. Different grades of metamorphism yield different metamorphic mineral assemblages. As grade increases, recrystallization produces coarser grains, and neocrystallization produces mineral assemblages that are stable at higher temperatures and pressures. Geologists refer to metamorphism taking place while temperatures and pressure progressively increase as prograde metamorphism. As grade increases, metamorphic reactions release water, so high-grade rocks tend to be drier than low-grade rocks. This means that minerals in high-grade rocks do not contain minerals with OH in their chemical formulas, whereas minerals in lower-grade rocks may. To understand prograde metamorphism, consider the changes that a shell undergoes during mountain building as it travels from a location near the Earth's surface to a depth of 30 kilometers below the surface. The clay flakes in shell lie more or less parallel to the bedding plane. Under low-grade metamorphic conditions and differential stress, the shell transforms into slate. In slate, the clay flakes grow larger, become better formed, and align parallel to the cleavage plane. As metamorphic grade increases a little more, the clay flakes decompose and new crystals of fine-grained white mica as well as new crystals of chlorite and quartz grow, transforming the rock into phyllite. Under intermediate grade conditions, the minerals in phyllite react and decompose, yielding atoms that combine to produce large crystals of mica, such as muscovite and biotite, as well as other minerals, such as garnet. The reactions also release water, which escapes. In our example, metamorphism takes place under differential stress, so the micas grow wide with the preferred orientation, and the rock becomes a schist. During metamorphic reactions under high-grade conditions, yet another assemblage of minerals forms. High-grade rocks do not contain much, if any, mica because mica contains OH and tends to decompose and release water at high temperatures. In fact, high-grade rocks typically includes water-free minerals such as feldspar, quartz, pyroxene, and garnet. As mica disappears, the rock loses its schistosity, but may have gneissic layering. We can represent the concept of prograde and retrograde metamorphism as a path plotted on a pressure-temperature graph. As a rock is buried progressively deeper, temperature and pressure increases. The rock follows a prograde path on the graph. We see progressive changes. Recrystallization causes mineral growth. Neocrystallization results in a new mineral assemblages, and mineral changes release water. Later, as uplift and erosion move the rock back towards the Earth's surface, it follows the retrograde path. Geologists have developed techniques to determine the times at which a rock reached particular locations along the pressure-temperature path. In this figure, a capital P, capital T, small t path for a hypothetical rock. Capital P is pressure, capital T is temperature, and small t is time. The dates in the parentheses indicate the time at which the specified pressure and temperature conditions were achieved. P subset M is the peak pressure, and T subset M is the peak temperature. We can represent the approximate conditions under which the rocks of a metamorphic facies form by using a pressure-temperature graph. Each area on the graph labeled with the facies name represents the approximate range of temperatures and pressures in which mineral assemblages characteristic of that particular facies form. For example, a rock subjected to the pressure and temperatures at point A, 4.5 kilobars and 400 degrees centigrade, develops a mineral assemblage characteristic of the green schist facies. This facies mineral assemblages commonly contain chlorite, a green mica. As the graph implies, the boundaries between the facies cannot be precisely defined because the transition between facies are gradual. So in this figure, the common metamorphic facies, boundaries between the facies are depicted as wide bands because they are gradational. Note that some amphibolite facies rocks and all granulite facies rocks form at pressure temperature conditions to the right of the melting curve for wet granite. Such metamorphic rocks develop only if the protolith is dry. The presence of certain minerals known as index minerals in a rock indicates the approximate metamorphic grade of the rock. A line on a map along which an index mineral first appears is an isograde, from the Greek iso meaning equal. All points along an isograde have approximately the same metamorphic grade. Metamorphic zones, the region between two isogrades, are named after an index mineral that was not present in the adjacent lower grade zone. To compare rocks of different grades, you could take a hike in the eastern United States from central New York State eastward into central Massachusetts. Your path starts in a region of unmetamorphosed rocks and takes you into the internal part of the Appalachian Mountain Belt, which contain high-grade metamorphic rocks. As a consequence, you cross several metamorphic zones. Let's now examine the wide range of geologic settings on the Earth where metamorphism takes place, as viewed in the context of plate tectonics theory. The conditions under which metamorphism happens differ among these settings because the geothermal gradient, the extent to which rocks endure differential stress during metamorphism, and the extent to which rocks interact with hydrothermal fluids varies with location. Types and settings of metamorphism in a metamorphic environment. Thermal, that is heating by plutonic intrusion. 2. Burial, increases in pressure and temperature by deep burial in a basin. 3. Dynamic, shearing in a fault zone. 4. Regional, pressure and temperature alteration due to orogenesis or mountain building. 5. Hydrothermal, alteration by hot water leaching. 6. Subduction, where we have high pressure and low temperature alteration. And 7. Shock, extreme high pressure attending a bolide impact. Heat flows from the magma into the wall rock, for heat always flows from hotter to colder materials. As a consequence, the magma cools and solidifies while the wall rock heats up. In addition, hydrothermal fluids circulate through both the intrusion and the wall rock. As a consequence of the heat in hydrothermal fluids, the wall rock undergoes metamorphism. The highest grade rocks form immediately adjacent to the pluton, where the temperatures are highest, and progressively lower grade rocks form further away. The distinct belt of metamorphic rocks that forms around an igneous intrusion is called a metamorphic aureole, or contact aureole. The width of the aureole depends on the size and shape of the intrusion and on the amount of hydrothermal circulation. Larger intrusions produce wider aureoles. Geologists refer to the local metamorphism caused by an igneous intrusion either as thermal metamorphism, to emphasize that it develops in response to heat without a change in pressure and without differential stress, or as contact metamorphism, to emphasize that it develops adjacent to the contact of an intrusion with its wall rock. Because this metamorphism takes place without application of compression or shear, aureoles contain hornfels, a non-foliated metamorphic rock. Contact metamorphism occurs anywhere that the intrusion of plutons occur. In the context of plate tectonics theory, plutons intrude into the crust at convergent boundaries, in rifts, and during the mountain building that takes place when continents collide. As sediment becomes buried progressively deeper in a subsiding sedimentary basin, the pressure on it increases due to the increasing weight of overburden, and the temperature increases due to the geothermal gradient. In the upper few kilometers, temperature and pressures are low enough that the changes taking place represent diagenesis or lithification of sedimentary rock. But at depths greater than 8 to 15 kilometers, depending on the geothermal gradient, temperatures may be high enough for metamorphic reactions to begin and low-grade metamorphic rocks form. Geologists refer to metamorphism due only to the consequence of very deep burial as burial metamorphism. Of note, burial metamorphism destroys the organic molecules of oil. For this reason, oil drillers stop drilling when the bottom of the hole reaches depth at which burial metamorphism has begun. Near the Earth's surface, in the upper 10 to 15 kilometers, slip-on faults can fracture rock and breaking it into angular fragments or even crushing it into a powder. But at greater depths, greater than 15 kilometers, rock becomes warm enough to behave like soft plastic as shear along a fault takes place. During this process, the minerals in the rock recrystallize. We call this process dynamic metamorphism because it occurs solely as a consequence of shearing under metamorphic conditions without requiring a change in temperature or pressure. The resulting rock, called a myelinite, is extremely fine ground and has strong foliation that roughly parallels the fault. Dynamic metamorphism can happen anywhere that faulting occurs at depth in the crust. So myelinites can be found at all plate boundaries, in rifts, and in collision zones. Dynamothermal or regional metamorphism. During the development of large mountain ranges, in response to either convergent boundary tectonics or continental collision, broad regions of crust undergo compression and large slices of continental crust slip up and over portions of the crust along faults. As a consequence, rock that was once near the Earth's surface along the margin of a continent may end up at greater depth beneath the mountain range. In this environment, three changes happen. 1. The protolith heats up because of geothermal gradient and because of igneous activity. 2. The protolith endures greater pressure because of the weight of overburden. And 3. The protolith undergoes compression and shearing. As a result of these changes, the protolith transforms into foliated rock. The type of foliated rock that forms depends on the grade of metamorphism. Slate forms at shallower depths, whereas schist and gneiss form at greater depths. Since the metamorphism we've just described involves not only heat but also compression and shearing, we call it dynamothermal metamorphism. Because such metamorphism tends to affect a broad region, tends to even hundreds of kilometers across and hundreds to thousands of kilometers long, geologists also call it regional metamorphism. Erosion eventually removes the mountains, exposing a belt of metamorphic rocks that once lay at depth, so that now we can see it and walk across it. Hydrothermal metamorphism at mid-ocean ridges. Hot magma rises beneath the axis of a mid-ocean ridge so that when cold water sinks through cracks down into the oceanic crust along the ridge, it heats up and transforms into hydrothermal fluid. This hydrothermal fluid then rises through the crust near the ridge, causing hydrothermal metamorphism of rock floor basalt, creating a rock we call greenstone. Eventually, the fluid escapes back into the sea as vents known as black smokers. Greenstone is composed of minerals like chlorite and epidote. Metamorphism in subduction zones. Blue schist, a relatively rare metamorphic rock that contains an unusual blue-colored amphibole, forms only under conditions where there's very high pressure and relatively low temperature. Such conditions do not develop in the continental crust, for at the high pressure needed to produce blue amphibole, temperatures are also high. So to understand where blue schist forms, we must search for a geologic setting where high pressure can develop at relatively low temperatures. Plate tectonics theory provides the answer to this puzzle. researchers found the blue schist develops only in the accretionary prism that forms at subduction zones. They realized that because such prisms grow to be over 20 kilometers thick, rock at the base of the prism is subjected to high pressure due to the weight of the overburden. But because the subducted oceanic lithospheric beneath the prism is relatively cool, temperatures at the base of the prism remains relatively low. Under these conditions, blue amphibole can form. Because of shear between the subducting plate and the overriding plate, blue schist develops a foliation. It's also one of my favorite metamorphic rocks. Shock metamorphism. When large meteorites slam into the Earth, a vast amount of kinetic energy instantly transforms into heat, and pulses of extreme compression or shock waves propagate into the Earth. The heat may be sufficient to melt or even vaporize rocks at the impact site, and the extreme compression of the shock wave causes the quartz grains in rocks below the impact site to suddenly undergo a phase change to a denser mineral called coesite. The phase changes that take place in rock due to the passage of a shock wave represents shock metamorphism. When astronauts sampled the moon, they discovered that the regolith covering the lunar surface contains the products of shock metamorphism produced by countless impacts. When you stand on an outcrop of metamorphic rock, you are standing on material that once lay many kilometers beneath the surface of the Earth. How does metamorphic rock return to the Earth's surface? Geologists refer to the overall process by which deeply buried rocks end up back at the surface as exhumation. Exhumation results from several processes in the Earth system that happen simultaneously. Let's look at the specific processes that contribute to bringing high-grade metamorphic rocks from below a collisional mountain range back to the surface. First, as two continents progressively push together, the rock caught between them squeezes upward, much like dough pressed in a vise. The upward movement takes place by slip-on faults and by plastic flow of rocks. Second, as the mountain range grows, the crust at depth beneath it warms up and becomes softer and weaker. Eventually, the range starts to collapse under its own weight, much like a block of soft cheese placed under the hot sun. As a result of this collapse, the upper crust spreads out laterally. Stretching of the upper part of the crust in the horizontal direction causes it to become thinner in the vertical direction, and as the upper part of the crust becomes thinner, the deeper crust ends up closer to the surface. Third, as erosion takes place at the surface, weathering, landslides, river flow, and glacial flow together play the role of a giant rasp, stripping away at the surface and exposing rock that was once below the surface. Even after the peaks have eroded away, the record of mountain building remains in the form of a belt of metamorphic rock at the ground surface. Vast expanses of metamorphic rock crop out in continental shields. A shield is a broad region of long-lived, stable continental crust where Phanerozoic sedimentary cover either was not deposited or has been eroded away. As a result, the bedrock exposed at the Earth's surface today formed during the succession of Precambrian mountain building events that led to the original growth of continents.